Okay, good afternoon. So I'm basically done. I finished up last Thursday with pretty much all the conceptual stuff except for a little bit. So there's a little bit at the end of chapter 27 that I sort of just kind of told you enough that you could do your homework. And then also in chapter 29, there's a little bit I want to say that I kind of, just gave you in that announcement. So there's an announcement in B-Space that told you the sort of main idea, but I want to kind of flesh that out more and give you a little more detail on that stuff in chapter 29 too. Okay, so any questions about anything? So next week, you'll have a discussion section. I should announce this on B-Space, I guess, but on Monday, you'll have a discussion section. I'll say as usual, you'll basically get stuff back, and the GSI will answer questions. The GSI won't have anything like prepared to do, so just if you have questions from the study guide or from homework or quiz or anything else, you can get that addressed there. And a week from today, I'll have a kind of question and answer type lecture. I won't really prepare anything. So today I'll finish up these loose ends from 27 and 29, and I might start reviewing a little bit. And then on Thursday, I'll intend to review everything since the midterm. And then, like I say, next Tuesday, I'll just sort of be here to answer questions. So that lecture will be webcast, I believe. Is that right? Yeah, okay. That lecture will be webcast. So if you need to miss it for whatever reason. Okay, so let me get to this chapter 27 stuff. So last time, we talked about a two-sample z-test, right? Chapter 27 talks about two-sample z-test. And I addressed one situation when it can be used, and I didn't address the other one. I wrote it down, but I didn't say why, really. So a two-sample z-test can be used in either one of two situations. One is when you're comparing values, and these values I'm talking about could be either sums or percents or averages. From two independent simple random samples. And I said before, it could also be or samples with replacement. So just to clarify that, this is the most typical case is when you're comparing results from two independent samples. Like last time I did an example with a simple random sample from Cal faculty, comparing that to a simple random sample from Stanford faculty, and comparing the percentage Democrats for those two cases. So the values I was comparing were the percentage Democrat at Cal, in the Cal sample, I should say, and the percentage Democrat in the Stanford sample. Those were two independent simple random samples. If those samples were, for some reason, done with replacement, that would be a little bit weird. Ordinarily, when you take samples from a population, you don't want to, I don't know, you don't want to throw people back because you don't want to ask the same person twice. But if for some reason you did do the sample with replacement, you could also compare those values just fine. I guess also if you were doing something where the samples were not samples from a population per se, but something like maybe comparing results from one die to results from another die, and you want to see whether or not, or test whether or not the two dice have the same average, something like that. That's sort of implicitly a sample with replacement. The die doesn't change after every roll or anything. Okay? So any case like that where you're comparing two independent results, either with or without replacement, that's legitimate. And I'll just mention along the way, since the samples are done without replacement for a simple random sample, you ought to think about using the correction factor. Now, in the Cal versus Stanford example I gave, I sort of swept that issue under the rug by not even giving you the population sizes. Okay, so if I had given the population sizes and the sample sizes were at least 10% of the population, then in this case you ought to be using correction factor. And you might use it for one sample, you might use it for both samples. Doesn't really matter, okay? You calculate those two SEs separately and then combine them using the formula we used last time. Okay, so any questions about this case, this first case? Like I said, this is what we did last time. Okay, so the last two sections in chapter 27 talk about a different case. And I mentioned this kind of towards the end of last lecture, but I didn't really say why. So I wanted to say why today and do an example of this. The second case is when you're comparing results we're comparing values from two groups and the way that I would think about this is this sort of like, it's sort of like having a treatment group and a control group. That's the most common context for this kind of case, like treatment and control groups. Both selected randomly. Oops, selected randomly from one group. So basically you have one population, and from that one population, the treatment and control groups both come from that same population. Okay? So you might think of this class, for example, as being a population, and if I wanted to do some experiment on the class or something, I might randomly select half the class to be in the treatment group, half the class is in the control group. And in that situation, it's legitimate to use the same two-sample z-test. And so I'll just say here at the end, like, basically treat the same way as independent. Okay? So you treat these situations as being the same. Okay? And that, I need to explain a little bit why it's legitimate to do that. So in the context of this hypothetical case where I want to do an experiment on the class, let's suppose I want to do some sort of medical experiment in the class. So if we split class at random into two groups, and one group is unusually healthy, what would you expect you could say about the other group? So I sort of pick half the class, and this wouldn't really be random. But suppose I pick this half of the class, and this half of the class is for some reason just kind of randomly unusually healthy. Right? Those people in the class are more healthy on average. Then what can you say about this half of the class? What do you think? You want to? Yeah. Nothing. Any other thoughts? Agree? People agree? Disagree? Yeah. Well, he's saying that you could say it's just chance, but okay, so yeah, I agree. Yeah, this group is sort of at random, unusually healthy. That doesn't make you think anything about this half of the class? Yeah? Yeah, so you might expect that the other half of the class is on average unusually unhealthy, right? And that's right. So there's the bottom line here. So to make this a little bit more clear, maybe, unusually unhealthy, I'll just say compared to population average. Population average, which is the population is the class. Okay, we're looking at this class. So if you randomly had more healthy people over here, the other half of the class has to be less healthy on average. So by the same amount, right? If this half is like, however we're measuring healthiness, if this class is above average, then the other half of the class is going to have to be below average. So the reason why I want to point this out is that those two groups are not independent, right? This first case I have up here says that the two groups are independent, and that's important, okay? Here, if you take two groups selected at randomly from the same population, anything that randomly happens in one, like if you randomly pick out some people and you get unusually healthy people, you've prevented those people from being in the other sample. That's one way to think about it. So by taking out those healthy people and preventing them from being in the other sample, the leftover people, no offense, are going to be on average less healthy. Okay, so that's the issue here. Okay, so this is yeah. So there are two issues I'm going to describe. This is one issue. So what effect do you think that has on the standard error? So in this case, when we compare two independent values, if one group is just randomly higher, like say my Cal, if you think back to my Cal versus Stanford example, if the Cal sample just randomly happened to have an unusually high percentage of Democrats in it, then you couldn't say anything about the Stanford sample. The Stanford sample is independent. Okay? So in this case, the SE that we calculate from that formula from last time, I'll write the formula in a minute, but if you think about that formula, the SE calculation is right for this, okay? Now, I've said here that the other group tends to be in the other direction. How are we using that standard error? We're thinking about, when we compare, we're thinking about the difference between those two groups. So the independent case, the Cal versus Stanford case, we have these two random values. If one of them tends to be high, we can't say anything about the other one. And what we're looking at is the difference between those two, right? Here, if we look at one of them and it's unusually high, the other one's unusually low. So that difference between them is larger than you might expect if they're independent, right? So case one is, if one of them's high, you expect the difference to just sort of be about that. In case two, if that one's high, then the other one is pushed in the other direction, and so the random difference is sort of amplified. Okay, so this dependence will tend to make the observed difference more than if the samples were independent. So if we use SE calculation, SE difference calculation as usual, the SE will be too low or too high. So if we just pretend like it's the first case, but in fact it's not, in fact these things are dependent, then we should tend to observe a larger observed difference than if the two samples are independent. So if we just do the usual math, is the standard error that we use, will that be too big or too small? It'll be too small, because what's the SE trying to do? It's trying to tell you the likely size of the chance error. And the likely size of the chance error is actually bigger than you would expect. Okay? So this will mean that if we just just carry on as usual, do everything as if they're independent, we'll get a standard error, and that'll be too small. Another way to think about that maybe is that if we have a simple random sample from this class, so we take half the class at random, that's our control, our treatment group, and then we take a simple random sample of a bunch of people from a different class, those two things will be independent. So if the people in half the class here tend to be unusually healthy, then the other people from that other independent sample will just sort of be average. Okay? So the difference that we observe between those two will be some chance error for the difference, and this calculation would be correct because those would be independent samples. So what we actually have, the chance error that we actually observe when we take two samples from this class should tend to be bigger. So the standard error underestimates the real size of the SE difference. Okay? So that's one issue. Okay? Let me call this 1. So this dependence leads to this problem. And I'll put a question mark here because I'm going to come back to this and describe this issue, but I want to describe another issue. And actually, as I'll explain, these two issues are going to cancel. So second issue. If I take a simple random sample of half of this class and calculate the standard error, first of all, is that a sample with or without replacement? So I take half the class, random half the class. Without replacement. So if I take half the class, I'm sort of implicitly not going to look at the same person twice. I'm taking half the class, like these people, you're all different people. It's as though I picked you all, like one by one. Okay, so that's without replacement. And it's half the class. So I'll give you a clue about this issue. Is half the class bigger than 10% of the class? Yes, right? And it's without replacement. So what does that indicate that I should think about doing? Correction factor, right? So correction factor, so since sample is without replacement, and in this case, I've sort of explicitly divided it into two groups, like half, right? You don't have to do that. It might be like a third, 2/3, or whatever. But in any case, each group, I'll just say typically, you wouldn't have to do this, but each group is more than 10% of the class. Of let's say, the overall group, just to be a little more general, overall population. Maybe we should use correction factor. Okay. If we ignore this, SE we use would be too big or too small? So what would using the correction factor do? Would using the correction factor make our SE bigger or smaller? Yeah, it makes the SE smaller in general. Okay. So if we ignore it, then the SE we use would be too big, right? If we leave that out. Okay, so I'm going to put a little question mark here, just to think about these two issues here. So there's the dependence, and the dependence is something that's going on, between the two groups. It represents the standard error for the difference, and a sort of, I'll say, mistake in quotes, having to do with calculating the SE difference as though the two groups are independent. And ignoring that mistake would mean that the SE that you use would be too small. If you ignore this issue, the correction factor issue, the SE you use would be too big. Okay, so where I'm going with all this is that, in fact, these two errors cancel. And it's not like, it might seem like, oh, that's just kind of, you know, being sloppy or you know, saying like, well, since one's too big, one's too small, then we'll just pretend, you know, just ignore both of them and pretend like two wrongs make it right or something. But in fact, they exactly cancel. It's not like, it's not approximation or something. And we don't know quite enough in this class to see why they should exactly cancel, but I'll explain it a little bit intuitively. These two issues cancel. So we can treat this situation like two independent samples. And you can actually treat it as though it's two independent samples with replacement. Because you're going to ignore the correction factor. So you don't want to even think about these as being without replacement once you decide that these two issues are going to cancel. Okay, now let's think about why they cancel a little bit intuitively. The reason why this is an issue is that, again, like once I start picking people out of the class, if I get people that are unusually healthy, then those people are no longer going to be available to pick for the other sample. So that's the way the dependence works, is that if you get unusual people, if you start drawing unusual people in your first sample, those people are not going to be possible candidates for the other group, right? So that's how this works, and it has to do with dependence between those two groups. Well, really, the reason why you would use the correction factor is essentially the same dependence, but it's dependence within the one group. If I start drawing people and I start getting people that are unusually healthy, well, the leftover people that I still have to draw are unusually unhealthy. So the reason why you use the correction factor, in fact, is to correct for that dependence within the same group. So again, if you start picking people that are unusually healthy, even within that same group, there's dependence. That as you continue to pick people for your first group, in fact, the draws are dependent, and they're dependent really in the same way. That you just as you take people out, those people are no longer eligible. You're sort of changing the population. So as you change the population, you create this dependence both within one sample and between two samples. So these are two ways in which that dependence comes up. And like I say, you can sort of ignore both, and you'll get the right answer. So I would like you to know that this issue exists, or these two issues exist. But like I say, in practice, you just treat the situation just like you treat the other case that we've already done. And that's why I sort of didn't really care too much about making sure that I explained this before you did your homework. Because you can do all the math, without thinking too hard about it. One reason why I want you to understand these issues is because if I gave you a problem like, taking these two samples from the same class, I don't want you to make the mistake of using the correction factor, right? If you use the correction factor, you sort of spoil the fact that the two wrongs make a right, because you've by addressing this issue by using the correction factor, now you don't have anything to cancel this dependence. So now you sort of screwed things up. Okay, so you sort of do need to know this because you don't want to fall into the trap of thinking, oh wait a minute, this treatment group is without replacement and it's in more than 10% of the population, so I need to use the correction factor. You don't need to use the correction factor because this other issue is canceling it out. Okay, so questions, thoughts about this? Okay, so the book has this somewhat confusing picture box model. I want to explain that also. It's sort of part of the same story. So I'm going to kind of sketch the picture in the book, and then I will do an example and come back to it and explain in a little more detail. So just for comparison, recall this example from last time where we have Cal faculty sample there and Stanford faculty sample here. And I don't really need you to recall any more than that. You don't really need, this example had to do with the percentage of Democrats at each university. I don't really care about that, but I just want to point out what the box models look like in this case. We have a box model for the Cal sample, we have a box model for the Stanford sample, and those are independent. They're sort of clearly independent because there's no way that what happens in our Cal sample can affect what happens in the Stanford sample in any way. Okay? If we got kind of randomly lucky and had extra Democrats in our Cal sample, there's no reason why we should expect the same thing or the opposite or anything from the Stanford sample. Okay, so this is two independent simple random samples. So that's the first case, which I guess I just erased. So the second case, comparing values from two groups like treatment and control groups, both selected randomly from one group, one population. We don't have two boxes, right? There's only one population. We have a bunch of people, or subjects, or whatever, in the box. And from that box, we're going to take two samples. So we're going to think about that as taking a treatment group and a control group. Again, two samples from the same population. And the way the book deals with this is, it seems sort of weird and hard to get your head around, but let me just kind of address why it's necessary. Since these are two samples from the same group, when we look at the outcomes, suppose the treatment group is, I'm going to do a Botox story like the other Botox story, so I'll describe it maybe a little bit in terms of that. Suppose these people, treatment group, they get Botox and they improve a lot, and this group, the control group, they don't get Botox and they don't improve as much. Well, how can we say anything about a null hypothesis in that case? If in this sample we got a high value and in this sample we got a low value, what does that say about the box? Because they're the same, they're drawn from the same population. So you can't say, like in this case, you can say the null hypothesis says the percentage of Democrats in this box is the same as the percentage of Democrats in that box. Well, it doesn't really make any sense here to say the percentage of improvement is, the same in this box as it is in this box, because it's only one box, right? So the way that the book deals with this issue is to have everyone have two tickets. Or sorry, everyone has one ticket, but has two sides, right? So you have every person has a ticket with basically two numbers on it, and just labeling them A and B, arbitrarily. It's like X and Y or something. And we only get to see one half of those tickets. So essentially, if one particular person gets in the treatment group, we get to see what's on the left-hand side of the ticket, whatever the A is. Maybe it's a 1 or 0, maybe it's a number, whatever. We don't get to see this side. So essentially, we don't get to see what would have happened to that person if they had been in the other group. And if the person ends up being in the control group, the opposite is true. We get to see the right side of their ticket, but we don't get to see what would have happened to that person if they were in the treatment group. Okay, so now, when you think about doing a hypothesis test based on this box model, what you're really saying is that if the null hypothesis is true, essentially if the treatment doesn't do anything, the average of the A's is the same as the average of the B's. Okay? So you can actually say something about the tickets themselves. Now, a more kind of strong statement might be that if the treatment truly does nothing, if it actually makes no difference at all, then you might say that you might expect the A's to always be the same as the B's, right? Because the B represents what happens if you give the person nothing, put them in the control group, and the A represents what happens if you give them the treatment. So, sort of intuitively, you might say that those two numbers have to be the same for everybody. And that's a reasonable, rough, intuitive way to think about it, but it's actually not quite right. And I'll say why once I do the example, okay? But maybe one way to think about it really quickly is that some people might be helped by the treatment, some people might be hurt by the treatment, and really what you're saying is that they balance out, okay? That overall, the average of the A's is the same as the average of the B's. It's not quite necessary that those two numbers are actually equal all the time, okay? All right, so that's roughly how the book describes this situation. Okay, so I want to do any questions about this before I do an example? Thoughts? Okay, so let's do an example, and like I said, I think that'll help help you understand why that box model is what it is. Okay, so again, I'm going to do an example of this situation, comparing values from two different groups, like treatment and control, both selected randomly from the same, from one overall group or population. And my example is Botox. It's a continuation sort of the example I did with Botox and stroke recovery before. So this is part 2 of that story. And if you remember before, the evidence was pretty convincing, but there were these problems, okay? And the problems were that there was no placebo. There was possible sort of selection bias because the people that got into the treatment group, the people that got the Botox, weren't selected as like a simple random sample from some population. And then there was also what you might think of as sort of a non-response issue or a consent issue, that the people that consent to have Botox injected in their hands might be a little bit different than the people that don't consent. Okay? So essentially 3 issues there. So I'll address them again as we do this. So this experiment was done later, and it was intended to correct some of these mistakes. And what we have here is 126 stroke victims. And very roughly, these are the same kinds of stroke victims we had before, where they all have some problems with their hands. So same basic symptoms. As before. So if you remember from before, that was like they had pain in their hands, or they had trouble getting dressed, or they had trouble washing their hands. They have some problems in their hands from having a stroke. Okay, and so yeah. Okay, so I'll write down the data. So 64 are chosen at random for treatment, and the treatment is same as before, Botox injections in their hands, and 62 remaining get a placebo. And that's that. So we're referring to that as the control group. Okay, so one of those problems from the other one we've already dealt with, that these people got, the control group got a placebo. And actually, I'm sorry, I should mention here also that maybe this is obvious, but all 126 consented to getting either. So anytime you have some clinical trial like this, some experiment with human subjects, you have to tell them the design of the experiments. You have to tell them you might either get Botox injected into your hands, or you might get a placebo. You don't have to tell them which one, because you want to maintain the blindness. So this is subject blind. They don't know which group they're in. So yeah, again, you have to tell them what might happen to them, but you don't have to tell them which group they're in. And so these two groups are similar in the sense that they don't, hopefully the placebo has done its job of ensuring that people don't know what they're getting. They don't know if they've gotten Botox or not. Okay, so any questions about this part, the sort of design selection process part? Okay, so then let me draw the box model, and then I'll give you the actual raw data. So we have some population of 126 stroke victims. We have 64 over here for the treatment group, and 62 over here for the control group. And I'll just mention quickly, ordinarily they try to roughly divide them in half. I suspect that probably what happened here was that between the selection process and the end of the experiment, like they wait a little while after they get the injection and see if people got better, a few people dropped out for one reason or another. So they may have had like other medical problems that sort of like were a red flag, and they were just taken out of the experiment. These people are typically pretty old. It's possible that some of them might have died, that something happened, right, that made these numbers slightly different, okay? It's okay. It just, I just want to mention that if you wonder sort of like why do they not have the same number of people in each group, that's why. There's a little bit of time that passes between the selection and the randomization and then giving the Botox injections and seeing what the results are. Okay. So in the treatment group, basically we see two different possible things. A 1, so we only get to see one half of the ticket, right? We have this A, B story. We get to see either a left side of the ticket or the right side of the ticket. For the people in the treatment group, we see one of these two results. Okay? So the kind of crossed out thing on the right side is what would have happened to that person if they happened to be in the control group. And we never get to see what that is, right? We never get to see like both what happens if they get Botox and also what happens if they don't, right? Okay, so we get to see either one of these two things. So 1 means improved. Improved with Botox. And there were 40 of those. So 40 people improved, and so I guess the remaining 24 didn't improve. Didn't. And in this group, we see the right-hand side of the tickets, but we don't get to see what would have happened if they had gotten Botox. So there are people that look like this. These are people that improve given the placebo. There are 17 of those. And, so sorry, let me put the 17 there. 17 tickets like that. Those are people that improve with the placebo. And there are a remaining 45 that don't improve. Okay. So I want to just think a little bit about what all the tickets in the box look like. So I guess you sort of notice that it sort of looks good for Botox, right? In the treatment group, most of the people improved, certainly. And in the control group, most of the people didn't improve. And it looks fairly like a pretty big difference, right? So it looks pretty good, but sample sizes are small. We should probably do the math. But I just want to say a little bit about those tickets in the box and what all of them look like. So, also say possible tickets. So I have some tickets that look like this. Now, again, we don't ever get to see both sides of the tickets. So I'm speaking purely hypothetically about what this ticket means about this person. We don't get to see both sides, but this would represent a person that would improve no matter what. So it doesn't matter what you inject that person with, that person's going to improve. And there are going to be some 1-0s that improve with Botox, not with placebo. and there are going to be some 0, 1s. These are people that don't improve with Botox. But they do improve with placebo. Okay. And then finally, you have 0, 0s that don't improve no matter what. So I do want to sort of give you a plausible story about each one of these tickets. And in particular, if you look at the data, you might think, okay, there are probably some of these people that would improve either way. Looks like there are probably some people that are going to improve if you give them Botox, but not the other way. You might think, this is kind of a weird ticket. Why would someone not improve with Botox but improve with a placebo? They improve if they don't do anything, but somehow they're not going to improve if you give them Botox. Well, it's possible, I'm not saying it's true or not, but it's possible that you might imagine that Botox is sort of a poison. When you inject it, it might have some short-term inflammatory effect. It might make it hurt more in the short term, something like that. And so you might think that there are going to be some people that would say that they don't improve with Botox. They might sort of balance out, that this pain they get from the poison in the Botox might balance out the good effects of the Botox. So it sort of seems to that person like it didn't do anything. And then that person might, if you just left them alone or gave them something completely neutral, they might feel better than the Botox injection. So there might be some people that are like that. And then I think the other ones are sort of a little bit more obvious how that could happen. These are just people that they just are going to get better regardless. These are people that the Botox really does help, and then they wouldn't have gotten better without it. And then some people are not going to observe improvement either way. So I want to write that down because I'm going to start doing a hypothesis test, and I want to be able to talk about these 4 possible things that happen. Okay, so let's try to answer this question of whether or not Botox works as a hypothesis test finally. So did Botox work? Or can this be explained by chance? And along the way, I will sort of think about, like we did with the other example, think about any other possible explanations. So other explanations. So I'm only really explicitly in this question thinking about Botox works or can be explained by chance. But it's good to think about if there's anything else, like any problems with the experiment like we did before. Okay, so let's do it. So first of all, the null hypothesis says kind of the null hypothesis part A is our chance statement. So that says in some way that the results can be explained by chance. Okay, by chance. And what does that mean in terms of this box? Well, what that means in terms of the box is essentially that the percentage of 1s on the left side is equal to the percentage of 1s on the right side. And that's a little bit unwieldy compared to like the Cal versus Stanford example. So your null hypothesis may seem a little bit weird for these situations, but it sort of has to be that way because you only have one population, so you have to be a little bit careful. So percentage of 1s on left, or if you want to say for the A's, in box is equal to the percentage of 1s on the right. Or if you want, you could say it for the B's in the box. So I think it's important here that you say something about the box or the population and not just make a statement about the sample. If you kind of left that out, I might be tempted to not give you full credit because really, certainly you observe in the sample in the two samples, the percentage of ones over here is bigger than the percentage of ones over here for these ones and zeros on the right-hand side. But what you really care about is what's going on in the box, right? Just like the Cal-Stanford example, we can see that the Cal percentage is a little bit bigger than the Stanford percentage in our samples, but what we really want to know is what does it say about the populations. In this case, there's just one population, so we're talking about like the right and the left side. Another way to think about this is that you might think of it as like your chance of improving is the same whether you get in the treatment group or the control group. Okay? So this percentage of ones on the left is kind of like, you might think of it as the percentage of people that would improve if they got the treatment. This is the percentage of people that would improve if they all got the control, if you just left them all alone. Okay. Any questions about that, about the box? Okay, so the alternative part A is this chance statement. Something like it's not just chance. And I'll say Botox helps. And in terms of the box, that means that the percentage of ones on the left is more than the percentage of ones on the right. I'll just say that very briefly. On left in box is bigger. Percent ones on right in box. Okay, so that's sort of what it means for Botox to work or help, or something else. So I'll just say, briefly at the end, something else. And yes, I'll talk about this. I don't think there are really any good other explanations for this particular problem. And we'll sort of explain why at the end. Okay? So any questions about that? Yeah? Do I always want you to talk about the tickets in the box? I think you should for the null hypothesis at least, because the null hypothesis determines how you're going to do your math, right? And if you just said Botox helps here, I think that's okay. You don't need to write it all out for this. But I think you should explicitly write out what you're saying about the box for B, because it should be clear where your, kind of what justifies your math. What justifies yeah, so when we do step 3 and get the z value, why is it that the expected difference is 0? It's because of that, right? So that's why I think it's important to be a little bit careful about what you say in that part of the null hypothesis, is because that provides you with the justification for this next step. Okay, so the null hypothesis says the percentage of ones on the left is the same as the percentage of ones on the right. Tickets that are 1, 1 or 0, 0, for those tickets, clearly, they're just, the values were actually the same. So there's no problem there. Essentially, part of what the null hypothesis is saying is that these things have to balance out. That the people that improve with Botox, but not with placebo, those people, like the percentage of people that are like that, has to be the same as the percentage of people that are like this in order for everything to balance out. You might think kind of, I don't know, maybe not naively, but if you don't think about this very carefully, you might think that the null says that all the tickets have to look like this, which would sort of really mean that Botox actually does nothing, that everyone either is going to improve no matter what or not improve no matter what. That kind of literally means that Botox does nothing different than the placebo. But that really isn't necessary for what we're doing here. It's just necessary that everything balances out. It's the same percentage of ones on the left as it is on the right. So there may be some tickets like this. Okay. So questions, thoughts, anything else? Yeah. Should you always draw a box model? I think it's good for you. I won't take off points explicitly for not putting a box model in your problem, but you might get partial credit if you do things wrong, but at least you have a box model, okay? So, it's not going to, yeah. So I think it's good for you, and I think it does do something useful in helping you think about the problem. But I won't require it unless I ask for it. It's possible that I'll explicitly ask, make a box model, and then I want one. But in general, if I just say do a hypothesis test, I don't care if you actually do the box or not. Okay. Any other questions? Yeah. Are the zeros and the ones on one ticket dependent? So like if you're just thinking about the zeros and the ones on one side there, well, the draws are dependent because they're without replacement. So for example, if I randomly got a bunch of ones, if I start drawing tickets and say I'm looking at the treatment group and I get a bunch of ones, you might expect that the remaining tickets are more likely to be zeros, that you have just sort of taken out some of the ones compared to the overall percentage of ones in the box. So in that sense, there is dependence between the draws because they're without replacement. But it's different people. So the different people are independent in a sense. You know what I mean? So like whether or not you improve from Botox is independent of whether or not someone else is going to improve from Botox. Does that make sense? Okay. Okay, so let's get this Z. So there's a bit of math here. I think I'll just kind of go through it fairly quickly. It's essentially, Z is observed difference minus expected difference divided by the SE for the difference. So the top, what are we going to put on top? Any thoughts? Yeah. 40 minus 17 minus 0. Anyone agree, disagree? Seem okay? Yeah. Should we use proportions? Question? Any thoughts on either of those? Agree, disagree? Yeah. Percentage of ones in the treatment group minus the percentage of ones in the control group. Another suggestion. So that's the way I'm going to do it. Now, technically you could do this in terms of proportions. And really a proportion is like an average, right? It's like if you think about 40 out of 64, that's like adding up all these tickets and dividing by how many there are. That's an average, which you could do. I'm going to do this in terms of percentages. I've written the null hypothesis in terms of the percentages. Using 40 minus 17 is wrong. Why is it wrong? Anyone? Yeah. Good. He's corrected his own mistake. Good. So yes, they're different size samples. They're pretty close, right? So it's a little bit attractive to just think about the 40 minus 17. But what if this treatment group was like twice as big as the control group? Then there's really a problem, right? If the sample sizes are really different, then you really don't want to look at just the observed raw values, because of course if the treatment size is twice as much, well, of course you should expect to get more people to improve just randomly, right? Or just based on, even if they have the same percentage of ones, if you take more people for your treatment group, you expect more people to improve, okay? If you had like 1,000 people in your treatment group, of course you're going to get more than 17 people improve, right? Okay, so we'll look at it in percentage terms. All these will end up being in percentage terms. Observed difference, expected difference, SE difference. So expected difference will be 0. We expect the percentages to be the same. If you did want to use 40 minus 17, maybe I should back up. If you did want to use 40 minus 17, you could, but then you would not expect the difference to be the expected difference to be 0, because since the sample size is slightly bigger here, slightly bigger for the treatment group, you should expect slightly more people to improve with Botox, even if the percentages of ones are the same on both sides. So that just makes your life hard, and we'll never do that, okay? But yeah, so that's sort of an explanation of why that shouldn't be done. Okay, so let's finally do the math. Alrighty, so I guess I'll erase this. It's fine. Okay, so we're going to get two SEs separately and then combine them using that SE difference formula. So for the first group, the treatment group, we have percent of ones, is the observed percent, is 40 over 64. 40 over 64 times 100%, which is 62.5%. Sorry, couldn't find it. Okay. And the SD, and this is the sample SD. So we're using bootstrap method along the way here, which is fine. Sample SD is 1 minus 0 times square root of 40 over 64 times 24 over 64. Okay? So 40 over 64, 24 over 64, that comes out to be 0.48. I'll do the SE sum calculation along the way. SE sum is square root of 64 times 0.48, which is 3.87. SE percent is 3.87 divided by the sample size, 64, times 100%. And we get 6.05%. OK. So that's our Botox group. Now for the treatment group. For the other group, the control group, we have percentage of ones is 17 over 62 times 100%, which is 27.4. And SD, this is again the sample SD. So you might think of this as like, up there I'm estimating the SD of the A's. Here I'm estimating the SD of the B's. Right? There are a bunch of A's on the left-hand side. So we're doing the SD of these compared to the SD of these. Right? And so here the sample SD is 1 minus 0 square root of 17 over 62 times 45 over 62, which is 0.446. SE sum is square root of 62 times 0.446, which is about 3.51. SE percent is 3.51. SE sum divided by number of draws times 100%. And that is 5.66%. Okay, so what I got here separately is this 6.05 tells me the likely size of the chance error for the 62.5%. So the 62.5%, if I took a different sample, you might expect it to be about 6% different. Roughly the same here. We observed 27.4%, but if we took another sample, did the experiment again, we might expect to get a different result by about 6% for that. So overall, then, the SE for the difference between those two things is square root of 6.05 squared plus 5.66 squared, which all that comes out to be 8.34. Okay, and that's in percentage terms, the SE difference. Okay, so I guess I'll erase this. So I'm almost done with my math. And all that, I hope, like, except for this line is the only line that's new in chapter 27, getting the SE for the difference. So again, it's the first SE squared plus the second SE squared, square root of the whole thing gives us 8.34. And again, this is that second situation. We're comparing results from two dependent samples, but this treatment and control group gives this specific situation where we sort of treat it as though it's two independent samples. Okay? All right, so finally the z is going to be 62.5% minus 27.4%. So that's the difference in our observed percentages. According to the null hypothesis, we expect that difference to be 0. And divide by the SE difference, 8.34. So as I mentioned last lecture, I sort of, I think it's good practice to put this minus 0 there. If you left it off, it sort of looks like you're doing observed minus expected. And there's a tendency to just use the SE for that if you do this way. This way, I think it's totally clear that this is an observed difference, this is an expected difference, this should be SE for difference. Okay? So that comes out to be 4.23. So that's our z. Step 4 is to get the p-value. And this is almost off the table. If you look this up, if you look up 4.25, you get 99.9979 in the middle. So this here is 100 minus this divided by 2 is going to be 0.001%. And that's close enough to 0 that it's okay with me if you just sort of treat it as being essentially 0. Okay? It's 1/1000th of 1%. So essentially, it's extremely unlikely that we would ever observe a result this extreme just randomly. Okay? So our conclusion will reflect that. So the conclusion part A says a bit of statistical jargon. It's okay with me if you said either reject the null or reject the null at the 1% level is fine as well. For part B, it's okay if you say like not chance here. You can't say for sure it's not chance, but this is so astronomically small that I feel pretty comfortable just saying that's not chance. Okay? And conclusion, Botox works or something else. So let's talk again about the something else. So the other experiment we looked at had 3 problems. One was that there was no placebo. Here we have a placebo. So there's no kind of systematic way in which these 2 groups are going to be different because of what they got. That's one. Second one is that before there was sort of this kind of vague selection issue. We don't know how the people got selected to be in the study. Here, you don't really care where, you don't care so much about where the 126 came from because at least when you randomly put them into treatment and control, there's no bias in that process. Okay, so you might be a little bit worried that depending on where those 126 people came from, this method of using Botox may or may not be applicable to people in some other population. Okay, what we can say here is according to the null, in this group, there's a difference, right? In this group, there's a difference between the percentage of ones on the left, percentage of ones on the right. Will this work for other people who have strokes? Well, if they're like these people, it will, right? So, for example, if I had pain in my hands and had trouble washing them and had trouble getting dressed, I wouldn't be like, oh, give me some Botox, because I didn't have a stroke, right? So presumably, if I'm like those people, it's maybe a good idea to use Botox. But if you just have your hands hurt or something, you would not think that this would be generally applicable to people with the same symptoms, right? Okay, so that's just a little comment about that. Okay, so no issue there. And then the third thing we talked about was this consent issue. And everyone here consented to the same thing, right? So there's no consent difference between the treatment group and the control group, right? So we can be pretty sure that Botox works. And in fact, I said before, it's used, okay? Okay, so that took a long time, a little longer than I had sort of thought. Any questions? Yeah? Can you still get credit if you don't say or something else? If there's something else, then if I think it's reasonably obvious or you should kind of wonder, then you might lose points. basically, I don't think you should conclude this if it's not right. If like in the other, if I gave it the other example and you just said Botox works, I probably wouldn't give you full points for it. So, okay. Well, let's, I guess, do you want to take a couple minutes break? Are your brains full? How do you feel? Anyone care? Like a 10-minute break? I'm joking. I'm joking. Okay, let me just go through, and maybe we'll leave a couple of minutes early. Okay, so I just want to say a little bit about Chapter 29. There's basically two issues I want to address in Chapter 29. One of them is what's generally called data snooping or multiple tests. The book refers to it as data snooping. I sort of prefer talking about it as multiple tests because I think it's more kind of indicative of what is actually happening. So let's suppose we go back to our very first hypothesis test example with the guessing game with the cards. There are these 5 cards, ace, king, queen, jack, 10 of spades, and what I did in class, sort of guess which one will come up next. And I did it 100 times, and I said, how many times would I have to get it right to convince you that I'm doing better, I'm able to do better than guessing at random? Okay, so let's suppose that 100 people in the class all do this. 100 people in class each make 100 guesses completely randomly. Okay, so no one is psychic, no one cheats, anything else, okay? So the null hypothesis is true, okay? The null hypothesis says that you should get it right about 1/5 of the time, right? So the null hypothesis is true. And I'm going to write this in caps because we always assume the null hypothesis is true, right? Whenever we do the math, we're always assuming that whatever the null hypothesis says is true for purposes of doing the test and finding the z-value and all that. What I'm saying in this case is it actually is true. It's not just an assumption. It really is true. So my question then is, well, I guess let me say a little bit more before I ask you a question. People will get different numbers of correct guesses, right? We'd expect that people will get about 20 right. And if you remember back to this example, the standard error turns out to be 4. So if you just guess at random, you should guess right about 20 times, give or take about 4, maybe a little bit more. So if you get 30 right, like I did in my kind of hypothetical example, the p-value comes out to be a little bit less than 1%, and you reject the null hypothesis at 1% level, and you would conclude that you're not just guessing at random. So first let me ask this. Could that happen to anyone? Is it possible that you would get 30 right? It's possible, right? Okay. You might get more than that even. So my question is, my next question is, we agree that it could happen that you would conclude that you should reject the null hypothesis, which would mean that you conclude that you're not just guessing at random, you're able to do something better than guessing at random. So this is a mistake, right? In fact, the null hypothesis is true. In fact, you're just guessing at random. So it's possible that just randomly you get so many right that you reject the null. And I'll say reject null at 5% level, okay? So reject null at 5% level means you got a p-value less than 5%, right? So the question is, about how many people will this happen to? Any thoughts? Guesses? Yeah. So you say maybe 2 or 3 people would have this happen to them? I think he's saying that he thinks there's a 2.5% chance. Yeah? 5? What do you think? Any other thoughts? So the answer is 5. About 5. Okay, so why is that? Well, according to the null, the probability histogram looks like this, right? You expect to get about 20 right out of 100. And I'm not going to do any math here, but I just want to sort of think about this intuitively. I'm just going to draw that little tail there, and I'm going to say that it has an area of 5%. And now my claim is that if you get into this tail, your p-value is less than 5%, right? And a p-value less than 5% is exactly what's required to reject the null at the 5% level, right? You're going to reject the null at the 5% level exactly when your p-value is less than 5%. Okay, so if you get right at this line, and you get right at this line, what's your p-value? 5%. It's the chance of getting there or something more extreme. So if you hit that line exactly, then your p-value is 5%. If you are anywhere to the right, then your p-value is going to be less than 5%. So what's the chance of getting a p-value less than 5%? Well, it's the chance of getting in that tail, right? Which has area 5%. So it maybe seems a little bit circular, but I think this is kind of important to understand, to really understand what's going on with the hypothesis test, okay? In general, we're assuming the null hypothesis is true, and then we're finding this p-value. Well, what if the null hypothesis is true? If it is true, then we've set ourselves up to fail in exactly this way 5% of the time. So we sort of know that going in. You know, if we sort of understand what's going on, we should understand going in that we're going to make mistakes. And if we accept it, you know, this says we should make mistakes about 5%. If the null hypothesis is true, we should sort of accidentally, erroneously, mistakenly reject it 5% of the time. Well, maybe we should only reject the null when the p-value is less than 1%. Then we won't make mistakes as often, right? Or maybe we should only reject the null if the p-value is less than 1/10% or 100%. Then we won't make mistakes very often. But the problem is then you might miss some things in the other way. Like if we only reject the null when the p-value is less than 0.5%, well, in my example with 30 right, my p-value was a little bit more than 0.5%. It was, I think, 0.82%. So in that case, if you adopt a more strict rule and only reject the null when you're really, really far away, well, then you might miss some cases where, in fact, I'm psychic, but you didn't detect it because you were only willing to reject the null when you get less than 0.1% or 0.5% or something really far away. Okay, just like some people when I said that example, some people said, oh, you need to get them all right. Well, okay, if you adopt that as your rule, then you'll miss out on rejecting the null and concluding that some people are able to do better than guessing at random when they only get 50 or 60 right? So this line is arbitrary, and there's this sort of give and take here. If you adopt a more strict rule, you don't make these mistakes as often, but there's another kind of mistake that you can make the other direction, okay? And you don't need to know this. This is called a type 1 error. The other thing's called a type 2 error. You don't need to know that. But if you've ever heard of those terms, that's what's going on here. Okay, so yeah, so this, right? Okay, so I think what I want to do here is, I was going to talk a little bit more about this one, but let me just talk about the other thing in chapter 29, and maybe I'll give another example of this thing on Thursday. This is the main idea here is, well, I'll say one more thing about it. If you do multiple tests, the idea is if you do multiple tests, you should expect to get these mistakes as a sort of regular thing. If we did this in class and 100 people did this thing and a few of them, maybe 5 people, we're like, oh, wow, I'm psychic. It's so exciting. Well, that's not really right, right? And I think if you did this and you actually had this happen to you and you got like, you know, maybe 28, 29, 30 right, you couldn't help but feel lucky, okay? I think that what would happen to you is you would feel like, whoa, something's going on. I'm so lucky. And, you know, that sort of is the psychological rejection of a null hypothesis in a sense. You get a result that seems like it's not due to chance to you, right? When in fact, it is just random. Okay, so let me just really briefly say the last thing, which is a two-tailed test. Two-tailed or two-sided test. Actually, the description in the book is pretty good of this, so maybe I won't talk a lot about it. But the idea here is that if the problem doesn't specify a direction, then, and this is essentially what I wrote in that announcement, I guess, then neither should the alternative hypothesis and p-value should be doubled. So let me just really quickly give you an example, just a kind of intuitive example. So I wonder if a die is fair. So I roll it, say 100 times. Now, if it rolls too high, at some point I'm going to conclude that it rolls too high, then it's not fair. If it rolls too low, I'm also going to conclude that it's not fair. Okay? So if you think about what's going on here, the null hypothesis says that the die is fair, and if it's fair, it has an average of 3.5. And if I got a result either up here or down here, then I would conclude that it's not fair. So since I would reject the null on either side there, my p-value should reflect that. And so the p-value should be, like say the data is here. Or just as well, the data could be here. When you get your p-value, it intuitively means the chance of getting data like you got or more extreme, assuming the null is true. Well, really, those 2 points are just as extreme. They're just as far away from the null, and they would make you conclude the same thing. Okay? So since that's true, there or more extreme should include both. So p-value is both of those put together. Now, the reason why this doesn't come up for something like the Botox case is that I'm only going to conclude the Botox works if I get a result that's better than the control group. So I only really look at one tail in that case. And every example I've done so far, I've been pretty careful that the way that the problem is written specifies a direction. Cal percentage of Democrats is bigger than the Stanford percentage of Democrats. I'm able to do better than guessing at random. All those kind of imply a certain direction. Okay? So the alternative hypothesis specifies a direction, and the p-value should be one-sided in that case. Here, the alternative would just say it's not fair. The average is not 3.5. It wouldn't specify it rolls too high or it rolls too low. It would just say it's different than 3.5. Either above or below. Okay, so I'm sorry I didn't finish. I intended to finish actually early. I actually finished a little bit late. Okay, so I'll talk about these just a little tiny bit more on Thursday, and then I'll just review. Okay? All right, bye.